Hello, and welcome to Physics with Ariel. I'm your host, Ariel Mobius, and today we'll be talking about charges falling from the sky. We'll start by looking at this picture. At first glance, it seems pretty obvious that this would just be lightning. And while that would be valid, that's not what we're looking at in this case. As very established physicists, we won't call this lightning. We are going to call this a charge flowing through a parallel plate capacitor. Why would we say this? Don't trust me. Let's figure this out together. Let's first remind ourselves of the definition of capacitance. It's the ability of an object to store charge. So how do we go about calculating capacitance? Well, first, like always, we build a model. And then we can calculate the electric field in this model. Once we have that, we can calculate the change in potential. And then finally, using our new formula, Q equals CV, we can calculate capacitance. So let's go about making this model. First, we'll draw the sky and the ground as two blocks, as they are. We'll add in a little cloud, make it seem a little bit more realistic. Our cloud will have a negative charge, and our ground will have a net positive charge because of the lightning situation. So where will the electric field lines go? Well, they'll be going towards the negative charge. Now let's draw in some surface charge densities. So because the sky and the ground are interacting, their surface charge densities will actually be the same. Let's call it sigma. And what is the surface charge density? Let's remind ourselves that surface charge density is just the charge over the surface area. Now let's take a closer look at what's going on in, say for instance, the ground. So we'll draw the ground as a little 3D block, and we'll make a Gaussian surface inside of that block. This will help us calculate the electric field in this area. Now we'll draw in our normal vector to the surface, and we'll draw in some electric field lines. Notice how they're going from the up, because they're going towards the negative charge of the cloud. Then we'll define this area of the surface as A, and we'll create a coordinate system. Now we're ready to apply Gauss's law, namely that the integral of the electric field over the area is equal to 4 pi times the charge enclosed in that area. Since we know the area and the charge enclosed, we can simplify this equation a little bit. Now we can do the same thing for the upper half, but now we're going to have some interesting sign changes that we're going to look at. So let's draw our quick Gaussian surface. It's going to be facing down this time, and now our normal vector is going to be actually facing the opposite direction of our electric field lines, because they're, again, still going to be pointing towards the negative charge. And this means that when we do Gauss's law, we're going to have this negative sign in front of the E dot dA, because the normal vector and the electric field lines are in opposite directions. And then we'll also have this negative charge in front of the sigma, because it is a negative surface charge density. So basically, all of this means that we'll get the same signs as we did before when we did the electric field calculation for the ground, and so then when we add them up, they'll scale. And this makes sense if we look at the picture from before. And then we can remember what the definition of surface charge density is and get our electric field. So now that we have our electric field, we're already on step 3 of our list of things to do. What's next? Calculating potential. So if you'll recall, the formula for potential is this really nasty looking integral of the electric field over ds, a path. But because of our geometry, things really simplify here. So what ends up happening is that the integral of this, it ends up just being E times d, the distance between the Earth and the sky. So then we can just plug in our formula that we got for the electric field right above, and then we get this really snazzy looking formula for the potential. And now for the last step. Here we make use of our cool formula that Q is equal to CV, and then since we know both the potential difference and Q, then we can calculate the capacitance. Here you can verify that everything we just did really does match up with a parallel plate capacitor. Okay, so I know I told you we were done, but I promise this next part's just really exciting. We're gonna plug in some real numbers. So let's first just start off redrawing our diagram. We'll draw the ground, the cloud. We're gonna give this cloud an actual real life area this time. It's gonna be 10 to the 10 centimeters squared, and we'll say the distance between the grounds and the cloud is 8 times 10 to the 4 centimeters, or 80,000 centimeters. We'll use our formula for capacitance that we just derived above, and we'll plug in these numbers, and then we get that our capacitance is around 10,000 centimeters. For reference, like most cell phones that have a capacitor, it has a capacitance of around 50 centimeters. So this is pretty huge. But if you think about it, this really does make sense because a cloud is pretty pretty big, and so it has a lot more ability to hold charge than the cell phone would. So before we end today, let's quickly go over what we learned. So the first thing we covered was how to use Gauss's law to find the electric field on an infinite plane. And in our case, our plane wasn't really infinite, it was just a really big cloud. Our second thing that we covered was calculating the potential from the electric field. And then the last thing was Q equals CV to calculate capacitance. Thank you so much for coming. I hope to see you again sometime soon.